Well, welcome back to our next review topic. Today we're going to focus on the words differentiable and continuous. So let's start with continuous. So the two things that pop in my head when I hear continuous is that I think a function has no holes or breaks and no vertical asymptotes. Now it can, however, have a horizontal. Alright, so let's just be clear. Horizontal asymptotes are okay. So let me give you a quick sketch. This function would not be continuous. Okay, certainly the limit exists. My pen is goofy here. Because when I approach from the left and from the right, I'm reaching the same spot. But because this hole's here, basically it's like I can't cross, I can't get over that hole. So this function is not continuous because there's a hole or break. Now let me show you a quick example with the asymptotes. I can certainly draw a function that has a horizontal asymptote that is continuous. So as I go from the left to the right, I have no holes or breaks, so this is definitely a continuous function. Now it wouldn't work that way if it was a vertical asymptote because there would be a hole or break. When you're asked to justify if something's continuous, you need to have the correct notation. And let's box this in. This is what they're looking for. The limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x has to equal f of a. So take note that whatever limit I'm approaching, that's the letter I'm using. If this is a and this is a, then I need to have f of a at the end there. And basically what that's saying is when I come in from the left and I come in from the right, whatever that intended height is a closed circle. Okay, I'm implying that that's a closed value. Now some people like to shorten that up. If the limit from the left is equal to the limit from the right, you can just say the limit as x approaches a of f of x is equal, oh Jesus pen, to f of a. Alright, so that's kind of the shortened version, but most people prefer writing out the left, the right, and f of. Alright, so let's focus on the word differentiable. If something's differentiable, we're just saying that the derivative exists. And graphically, that would look like no corners or cusps. So I just want to be clear, a corner should be a right angle, and a cusp should be more of like a pointed-y, brackety type thing. So this is my corner, and I would say this is not differentiable, and neither is this cusp. Okay. Now, notation-wise, we have to be clear on notation. This has been a popular theme on the past couple exams, understanding the notation of differentiable. It's very similar to that of continuous, or a limit exists, basically. I would say a limit as x approaches a from the left, this time not of f of x, but of f prime of x, has to equal the limit as x approaches a from the right of f prime of x. So basically, I need to say not their left and right sides exist, but their left and right slopes are the same. And the whole point is to catch those two slopes. I just want to point out one other graph that I think is fairly sneaky that some people miss. And it's the graph, whoops, that looks like this. Let's go ahead and, oh my. Looks like this. Oh, there it goes. And the question is this function differentiable? Now, you might be thinking yes, because there's certainly no corners and no cusps. But right in the center here, if you were to draw in a tangent line to represent the slope, what is the slope of a vertical line? Hopefully you're saying that the slope does not exist when it's a vertical line. So this is another example of a function that's not differentiable, even though it doesn't come to a corner or a cusp. This slope also is not differentiable, or this function, I should say, is not differentiable at this point here, okay, because it has a vertical tangent line. All right, so determine the values for a and b such that f of x is differentiable. And they give this nice piecewise function, and you're using this piece of the function when x is less than 2, this piece of the function when x is greater than or equal to 2. So first and foremost, you should be pulling out the word differentiable. That is the calculus word. And when I see the words differentiable, the first word that should pop in is derivative, and I'm going to set their derivatives equal. So let's carefully take the derivative of the left side. Ax squared should be 2ax. That b is a constant, 1 is a constant, so their derivatives are 0. Take the derivative of the right, so that's 3bx squared minus 3a. Now remember, you actually know a value. You know that x is equal to 2. So if I plug x equals 2 in, and I'll make a note here. This is true and x is 2. That was the breakpoint. So I should get 4a equals 12b minus 3a. And I can't go too far. I'm just going to at least put the a's on the same side. I'm going to say 7a equals 12b. All right, now I'm not even close to being done. All I took care of the word is differentiable. But remember, differentiable obviously means derivative, but it also implies continuous. So now let's take care of the word continuous. And continuous just means the left side equals the right side. So I'm going to set my ax squared plus b minus 1 equal to bx cubed minus 3ax. And again, all of this is true when the x value is 2. So I should get, that'll give me 4a plus b minus 1. 2 cubed is 8, so that's 8b minus 6a. And again, I'm just going to put the a's and b's on the same side. So I get, add my 6a over, I'm looking at 10a minus 1 equals 7b. All right, at this point, I just want to clarify the two equations I have. I have my differentiable answer and my continuous answer. And I'm just going to rewrite those for myself over here. So I know 7a is equal to 12b, and I know 10a minus 1 is equal to 7b. So at this point, the whole problem now is about substitution. Okay, it doesn't matter which equation you solve and which one you sub in. At the moment, I don't know if one's easier than the other, but you have to solve for either A or B in one equation and substitute it into the other. So, to me, there's less in this one on the left here, so I'm going to solve just for A. I guess it doesn't matter. So I'm going to say A is equal to 12b over 7. And now that I know what A is, I'm going to substitute it into the A in this equation. So I've got 10 times 12b over 7 minus 1 equals 7b. And I'm just solving the simple equation. That gets me 120b over 7 minus 1 equals 7b. I prefer the method of killing the fraction. If I want this 7 to disappear, I have to multiply by 7, which then I'm going to multiply every term by 7. So I've got 120b minus 7 equals 49b. I'm going to subtract my 49, or I'm sorry, I'm going to subtract my 120b. So I've got negative 7 equals negative 71b. And to solve for b, I'll just divide that over. So I've got 7 over 71. Not the friendliest, but I wouldn't say anything harder than you do in Algebra 1 minus the derivative step. Once I know what b is, I simply need to go get a, and I'm just going to find the simplest equation I can, and to me that's this guy here. A is just equal to 12b over 7, so I'm going to carry that down. A equals 12b over 7. So I know A is equal to 12 times 7 over 71 divided by 7. And this is just my way of cleaning it up. I'm going to say that's 12 times 7 over 71. Instead of saying divided by 7, I could say times 1/7. And then my 7s would cancel, and I basically get A equals 12 over 71. Okay, so not the prettiest math in the end, but there's nothing harder than what we do in Algebra 1. We're solving two equations and substituting them into one another. All right, last little part I want to work on is just, how we're going to write this up. Is g differentiable at x equals 3? And I hope you know the answer right off the bat is no. Clearly, please don't say that's a corner. That is a cusp. Okay, when it has it's not a 90-degree angle, it's a nice sharp point. I just want to be clear that you can't write down because g is a cusp. You don't get any credit for that. You have to use that definition. So I would say, is g differentiable at x equals 3? No right off the bat. And the only justification they're going to take is that limit definition. So the limit as x approaches 3 from the left. Now be smart, you're talking about g, but you're looking at its slope of g prime of x does not equal the limit as x approaches 3 from the right of g prime of x. Okay, so I just want to focus on that notation. All right, well, hopefully we've got a good base for tomorrow about continuous and differentiable, and we'll see you in class.